Welcome back. In this video, we will talk about internal energy, enthalpy, and then start from there, we will move on to specific heats of ideal gas. Okay, let's start from internal energy. Internal energy. To calculate the change of internal energy, we have this equation, delta capital U. Delta means change. Capital U is the internal energy. The change of internal energy is a function of, first of all, the mass of your subject, and second is a function of the change of temperature. The bigger the temperature change is, the bigger the change of internal energy is. And then one last thing, a coefficient, it's called CV. CV. CV is specific heat at constant volume. We can use this equation to calculate the change of internal energy. Next step, let's divide both left-hand side and right-hand side by mass. So capital U divided by mass, it becomes lowercase u. And then right-hand side becomes CV times delta T. Okay, so now if every step length is very, very small, from calculus class we know we can change delta to derivative. So du is equal to CV times dt. And from here, we can find the definition of CV. The definition of CV is du over dt. That's the definition of CV. The name of CV is specific heat at constant volume. The unit for CV that we usually use is kilojoule per kilogram per Kelvin. Okay, and then let's start from du equal to CV times dt again. We start from this equation. Okay, we start from du is equal to CV times dt. And from here, what we can do is to solve this ODE by integrate both left-hand side and right-hand side. CV dt and integrate. Okay, and also from here, we can find U is equal to CV times dt. Left-hand side is pretty straightforward. Left-hand side just becomes U, and then we keep right-hand side. And then if your CV is a constant, what's going to happen in this equation? If CV is a constant, U will just become, lowercase u will just become, if you can take CV out of the integral sign, and then what is left is just temperature. If CV is constant, you can calculate U by using this equation, CV times T. Okay, so here we develop two important equations. First one is the definition of CV. Second one is if CV is constant, you can use this equation to calculate U. So Here you have option 2 to look for internal energy. Instead of going to the tables, you can use this equation if you have an ideal gas. And Cv is usually constant because Cv is a material property, even though the value of Cv is usually a function of temperature. However, the change is very, very small. So usually in this class, we always treat Cv as a constant, unless otherwise stated. Okay, so now after internal energy, we do something very, very similar, but this time we start from enthalpy. Okay, first of all, delta H. What is the definition of enthalpy? Can you remember? The definition of enthalpy is internal energy plus capital U plus pressure times volume. This is the definition of enthalpy, capital H. And to calculate the change of enthalpy of ideal gas, we have an equation very similar to before. First of all, it's a function of the mass of the substance. Second, it's going to be the function of the change of temperature. The bigger change of temperature is, the bigger change of enthalpy is. And then the last one, we need a coefficient. This time, instead of Cv, it's called Cp. And Cp's name is specific heat at constant pressure. It's also a material property, just like Cv. Okay, so next step, what we're going to do is to divide both left-hand side and right-hand side by mass. Delta, capital H over mass, it will become lowercase h, specific enthalpy. And right-hand side becomes Cp times delta T because mass goes away. Okay, so now just like before, if we know every step length is very, very small, we can change delta to differential. So this equation becomes dH equal to Cp times dt. And then just like before, here comes the definition of Cp. From algebra, we know Cp is equal to dH over dt. And this is the definition of Cp. Very similar to the definition of Cv. If you take a look, the only difference is for Cv is derivative U, but for Cp is derivative H, specific enthalpy. Okay, so the name of Cp is specific heat at constant pressure. And the unit for Cp we usually use is the same as the one we use for Cv, which is kilojoules per kilogram per Kelvin. Okay, and then just like before, we start from this equation again, dH equal to Cp times dt. dH equal to Cp times dt. And from here, what we can do is to integrate both left-hand side and right-hand side. And again, left-hand side just becomes h equal to integral Cp times dt. Same as before. If Cp is a constant, what's going to happen? The integrand Cp is constant, so you can take Cp out of the integral sign, and then what is left is just delta T. If you're dealing with ideal gas and Cp is a constant, then instead of going to the tables, you can use this equation to look for specific enthalpy. It's equal to Cp times delta T. And just like before, Cp is a material property which usually depends on temperature. And again, because the change over temperature is so small, so usually in this class, we always assume Cp is a constant, unless otherwise stated. Alright, so that's Cp and Cv. And now we talk about the relation between those two specific heats. What is the relation between Cp and Cv? Let's start from the definition of specific H, specific enthalpy H. The definition of specific enthalpy H, lowercase h, is lowercase u, which is specific internal energy, plus pressure P times specific volume nu. This is the definition. And now let's keep lowercase u in our equation. However, if you go back to ideal gas equation, what is P times nu equal to? Let's go back to ideal gas equation. Okay, if you take a look under alternatives, alternative number 1, P nu can be rewritten to RT. So we can rewrite this P nu in my right hand side into RT. It comes from ideal gas equation. Okay, and next what we do is to take the derivative of both left hand side and right hand side. So left hand side becomes derivative H. Right hand side becomes derivative U plus RT. And then we can expand right hand side du plus dRT. And then we can continue, keep du. And however, R, which is gas constant, if R is constant, you can pull it out. So it's R times dt. Okay, so now what we're going to do is to divide every term by dt. So left hand side becomes dH over dt. T is temperature. And then right hand side, this is left hand side, this is my right hand side. So right hand side becomes du over dt plus R. Divide every term by dt. So this is what I get. Alright, so now let's take a look. What is du over dt? And what is dh over dt? And what is du over dt? Let's go back. What is dH over dt? If you take a look inside this box, dH over dt is the definition of Cp. So left hand side becomes Cp. What is du over dt? Let's go back. Du over dt. Take a look at this box. Du over dt is the definition of Cv. So the first term in the right hand side becomes Cv. So this is the first relation between Cp and Cv. Okay, and next we introduce another one. We introduce Cp over Cv and we give it a name. We call it K. K is the ratio of the two specific heats and is defined as Cp over Cv. So now with two unknowns, Cp and Cv, we have two equations. So now we can solve for Cp and Cv. Cp can be rewritten to K times R over K minus 1. Cv will be equal to R over K minus 1. One thing I want to point out here is if you take a look at this equation, Cp equal to Cv plus R, what is R? R is gas constant and it's always a positive number. So Cp will always be bigger than Cv. So the ratio Cp over Cv, which is K, will always be bigger than 1. Okay,